All ASKAP observing is done on the Kira 10 machine, usually via the :1 VNC window. The VNC password is the usual ATNF observing password available on Venice via the password request command. If you cannot connect to the VNC, it is worth checking that it is actually running. If you SSH as VLBI into kira10.atnf.csro.au, you can check if there is a VNC process running using the grep command. You should see a result like this. If it is not running, you can run the start VNC command. That should then in the background start a VNC server, and then you can start your VNC client. Once you're connected to the VNC, you need to start up the ASKAP GUI control. You need to cd in the directory called askap/run and run the command askap, then the name of the antenna you want to use. For L-band, we use AK7, and for X-band, AK32. However, Mike Kesteven's code uses the SETC number, which uses 26 for X-band and 19 for L. Unfortunately, the ASKAP numbering and the SETC numbering are different. In this case, we're going to use X-band, so we'll start up 26. This will start up ASKAP drive and a control GUI for that. It's the ASKAP drive xterm, which will run in the background, and then the GUI. The GUI you can enter simple commands from here. So at the moment the antenna is stowed and the drives are up. If we just type the command unstow, it will unstow the antenna. We can see that the drive pin is driving out. Typically when observing, all of these windows should be yellow, not red. If you have some trouble and the drives stay red, you can run the command drive off, leave it 5 seconds, then drive on. This often fixes any problems you have. We can now see the drives have come up and the antenna is out of stow. If we want, we can manually track a source from here. We can set the coordinates of either ASL or RADEC and put in the coordinates. So say 170, then just try track. The antenna will slow off in that direction. So it's not track at start. We can put in the coordinates of the source. Very strange. actually run a schedule, we need to use the VLBI drive command that is also run from the ASKAP run directory. We can then give it the name of the schedule we're going to run, which runs one level up in the schedules directory. Schedules typically have the name of experiment name -ak.psn. They use the same format as Parks. ASKAP drive then talks to ASKAP drive, and the antenna should start tracking. If all goes well, the antenna system should now run for the entire experiment with no problems. Unfortunately, the system is a little bit unreliable, so you do need to keep a close eye on what is going on. Typical things you need to monitor are that the drives are all on with no errors, and that while the antenna is tracking, this stack counter is slowly counting down and then resetting. If the stack counter freezes, it means the system is frozen and you need to restart. The same as if any of these lights go red, the drives have stopped. The typical workaround would be the antennas and drives have stopped. You stop the track, you kill VLBI drive with Control-C, then type drive off to turn the drives off. Leave it a few seconds and then drive on to restart them. It's only though if you see a drive failure, then you would restart VLBI drive and it'll pick up the schedule from where it should be. If however you find that the stack is not counting down, or that it seems like the whole system is frozen and is no longer pointing to the correct source, you need to restart everything, in which case Control-C VLBI drive, click quit on the GUI, and you'll find ASKAP drive is still running. So Control-C that, then you need to start from scratch again. Restart the ASKAP process to start the GUI and ASKAP drive. The drives will still be on and connected. Again, if any red lights here, turn the drives on and off, then restart VLBI drive. The antenna should start tracking again. Recording is done by a simple command line process. You need to manually decide where the data goes. There are 3 RAID disks on this machine. /int RAID 0, 1 and 2. When you start an experiment, make sure you choose a disk with enough disk space. You CD to that directory, and then you create a directory for that experiment, CD into that, then by hand run the command fix 14_record, give it the prefix of the experiment or whatever you want to use for the file names, time you want to record, and you also need to tell it the voltage level to set for the internal attenuators. Typically for X band 14 is right. The system uses an internal 14-bit counter, so you'll see that the RMS is quite high. A couple of thousand is about what we normally run it at. The system then converts it back to 2-bit. That gives a nice amount of overhead. While this is running, the things you need to check are that it's still ticking over. Standard deviation is reasonable, not too low, not too high. If it goes to a value of about 80, you have no signal. The other value to monitor at the very end here, this is telling you the difference in milliseconds between the implied VLBI time and the system time. It will never be identical and will occasionally fluctuate due to errors in the PC timekeeping. But if it is very large or increasing quickly, it means there is a problem with the recording. The only options there are either to try restarting or resync the maser. Ask someone to resync the maser. If you want to stop the system, you can Control C, but typing escape is safer, as it is guaranteed to trap the problem. Sometimes when you start px14_record, you get a DMA error. If you see that, just try a few more times. If it's persistent for more than say a dozen attempts to restart, you need to get someone to restart the kernel driver or reboot the computer. It's important to periodically come back and check that this is still ticking over, that you haven't actually accidentally exceeded the disk space available or some other problem with the recording. Similarly with the antenna drive system, it's important that every 15 minutes you still check the system is ticking over, as the ASKAP drive system is probably the least reliable in the VLBI system.